Hello, welcome to Group 23's midterm demo for our smart cooler. I'm Chautai Bunhaviseth.
I'm Matthew Schmidt.
I'm Thomas Wynn.
And I'm Michael Villarante.
All right,
Alright, so what exactly is the smart cooler that we're building? So to put it in more simplified terms without including all the engineering terminologies, it's basically just a cooler that improves on the quality of life towards the user experience. So what we'll be having is a special type of glass, polymer dispersed liquid crystal, to show the contents within the cooler without having to open the cooler at all. The product aims to be like a useful way to see what's inside the cooler and have some extra peripherals on the outside, such as a USB charging port and some temperature displays to see if everything inside the cooler is still cold enough. And in the next slide, we'll see a certain scenario that could be applied to everyday, parties, recreational activities. So here we have our user opening up the cooler and activating our motion sensor. You could be like, hey, we're out at a nice campfire. It's a little dark outside. You want to go inside the cooler. You look inside. Oh man, it's too dark. He's like, well, if you want to drink, oh, this is the motion sensor that solves that issue. Brings up a quality of life. The user doesn't have to like squint their eyes or like bring the drink close up to their face when they're trying to observe what they're looking at. Except we'll have lights. This isn't the final area. This is just a demonstration to see that the motion sensor and LED lights will be within. And then in our second scenario, we have our user trying to plug in or listen to their wireless headphones, but it ran out of charge. But for the smart cooler, that's of no issue. We have a USB charging port that will be right on top of the lid, easy plug in, and there'd be no issues whatsoever.
Uh, for the physical layout, on the left side, we have a picture of the top side of the cooler. For that, we have the solar panel as well as the LCD. We have a PDLC glass, the UV sensor, the button to turn on the light manually, and as well as the USB charging port. And on the image to the right, we have the inside of the cooler, which has the compartment for the battery as well as the solar panel controller. And then there's also the LED lighting that's going to be along the cooler inside. For our motion sensor test, here we have a 3.3 volt power that's connected to the microcontroller. From here, the motion sensor is communicating to the microcontroller to send the data, whether it's being like disturbed, like going open or closed. And from that information is being sent to the transistor, which is then going to switch on the power to the LEDs that are inside the cooler to either turn on or off. And for this LED power, we're using a 3.3 step up to increase the power. For our UV sensor test here, we have the UV sensor connected to the microcontroller, and from here, you can see the values are changing depending on the exposure of UV light that is being detected. And from there, the UV light will then transfer that information to the LCD to be displayed on the cooler.
Here we have the setup for a temperature and humidity sensor test. The sensor is setting its data to the microcontroller, which is then communicating the data to our LCD screen to display the information for the user. The sensor is using the 3.3 volts from our microcontroller for power, while our LCD screen is using a 5 volts from our step down of 12 volts from the battery. And there's a resistor of 220 ohms used for the brightness control of the screen, and then a resistor of 60,000 ohms that is in control for the opacity of the characters on the screen. And here we have our PDLC glass being tested for its time to activate. For our film, we wanted it to be able to quickly change from its opaque state into its transparent state. For this, we timed how long it took for the film to go from its off to its on state. In testing, the film was able to activate consistently for under 1 second. There are multiple trials that are done with the average delay between switching the two phases being under the 1 second. And in the final design, the glass will be connected to a switch that will give the user the ability to switch between the two states of the glass when they choose. In its on state, the glass uses around 12 volts that are supplied from the battery. And here we have our PDLC glass being tested for its opaqueness. We tried our best to accurately test the light levels from within the cooler, and with the only light source coming from where the PDLC glass was sitting. When testing the minimum values we obtained when the glass was in its off state were in the 60s, and when the glass was turned on, the max values we obtained were in the 150s. And with these values, we got an estimate of about a 60% opaqueness for a glass when it's in its opaque state.
Here we have our sensor statistics that were gathered through a continuous 10 trials each. They were recorded to showcase the accuracy of our sensors as per our engineering specifications. On the left, we have a table containing the results of our motion sensor runs. As you can see, the average time to activate was pretty instantaneous, and using a stopwatch to record the time shows us that. The data set was very close together, which lends itself to the low variance that was calculated here. And lastly, for this sensor was the average range of detection, which ended up being about 29.9 inches. For our UV sensor in the middle, the table in the middle, it outputs what is known as a UV sensor count, as seen at the top of the table. The average recorded UV count we obtained was about 195, and we used the UV counts to calculate the estimated UV index. The calculations for this is from the UV index conversion formula. This is shown below, and it was taken from the optoelectronics datasheet for this specific sensor. The average UV index we calculated after the 10 trials worth was 2.07, which is classified as low. Though at this time of day outside, the UV index reported through the UV Index Today website for Orlando, Florida was about 11.4, which is extremely high. We believe the differences between our measurements and the forecast could be due to differences in possibly cloud covering, sensor gain, sensor sensitivity, sample size, and this creates large changes when calculating and converting to a UV index. As we can see, our average UV index variance is very low at 0.03, showing that the dispersion of the UV index data was close together. Lastly, for our temperature and humidity sensor, we recorded the outside temperature and humidity and ended up comparing them with the local weather radar online for Orlando at the time of the runs, which down below we can see that all runs were recorded at July 5th at 1 p.m. And so our average recorded temperature was about 94.29 Fahrenheit and was very close to the weather app's report of 94 degrees Fahrenheit. The disbursement of the recorded temperatures were quite close, and this resulted in another low variance value for the temperatures. The same applies for the average recorded humidity compared to the weather app's humidity reporting, and the humidity data changed even less so with an incomparably low variance as shown below. So as we begin to approach the final stages of this project, our key objectives laid out right now is to obtain our PCB, which should be arriving very soon, and solder all of our components and connections to it. As mentioned before, we moved away from the 3D printing of the lid and are working with the machine shop and TI lab technicians with manufacturing our lid to the design we want. This, of course, comes with making sure we have final placement of all our components onto the cooler. And our biggest challenge right now is just balancing everything as deadlines approach and basically finishing up the manufacturing of our lid so we can start with the placement of everything within the cooler and on top. That concludes our midterm demo, and we are excited to show you the finished project in the future. Thank you so much.